Hey, this is Andrew McLaren. Today we're going to go over intermolecular forces. We're going to think about how you solve these problems and what you need to know. We're going to go over actually first some simulations, then the main idea, and a couple of these problems that look kind of like this. There's a lot of vocab words that you need to be able to work with, so I'm going to try and help you understand what those words mean, and then help think about how like the strength of the bond really is going to determine how much energy you need to put in to make it boil or melt, and how it's going to dissolve with similar things or not similar things. So we're going to be thinking about how things will dissolve as well. That's typically what they have you do with intermolecular forces, where you're thinking about, well, how much does this want to change to the next phase, or how much does this get stability if it's dissolved in like water or oil. That's the main idea of these problems. Before we actually try and solve these problems, let's think about what are prerequisites. So there's a number of things that you need to know for doing these types of problems. Like you need to understand electronegativity. You need to have some understanding of like bonds and orbitals, and like the chemical formulas. Like if I gave you something like CH4, you have to be able to know roughly what that is or be able to draw that in some way and be able to tell me what's going on with the electronegativity of the atoms in there based on the periodic table. That's very, very important for doing these problems. If you don't have that down, it's going to be very, very difficult. There's also a lot of vocab words that you're going to need to be able to define and like draw pictures of for each one of those things. And like I said, drawing a picture for this problem is basically how you do it. You have to think about what's going on with the orbitals, and the best way to do that is to draw out a model of the chemical. So what we need to do when we're trying to solve these types of problems, like something like this, is that we're going to need to draw out these chemicals and see what's going on with the atoms and their electronegativity and their orbitals and bonds. That's the main idea on these types of problems. It can be tricky though with all the different words. I'd like to start off with simulations because it really helps you to kind of play around with polar and nonpolar bonds and see what that does to the whole molecule. So we'll do that a little bit with this molecule, and then molecular shape we'll look at a little bit to review that. Then this is pretty good because it relates to biology a little bit, and this is going to talk about boiling point when things are polar and nonpolar, and kind of demonstrate that with the simulation. So let's go ahead and dive right to it. This first one is on, let's do molecular polarity first. So if we have two atoms and they're the same electronegativity, like let's say it's the same thing, like two fluorines, they're going to be evenly sharing the electrons. So it's kind of like, if you think about it, the charges are balanced out. Now, if we make one be more electronegative and one less electronegative, you can draw these symbols where this shows like this is a more negative side and this is a more positive side. You can also look at like the electron density, and you can say the electrons are mostly hanging around on this side and not very much on that side. There's a number of different ways to kind of look at this. But at the end of the day, when we have a bond, it isn't perfectly split between the two sides, the electrons. Like they're going to be hanging around one of the atoms more than the other. And when we have that, we have a bond that's polar. So if you see a symbol like this arrow on the top and the bottom, that usually is used to show that something is polar. And if you've got bigger difference in electronegativity, things will be more polar. So like fluorine and chlorine, they tend to be pretty polar when they are in compounds, when they're bound to other things. So you can kind of change this stuff. And also if I make the A more electronegative, then you can see that it's got more of that negative charge on it. So it's going to get more of the electrons, especially if B is very weak. So that's the kind of the idea, is that a polar bond is the electrons are not being evenly split between the two sides. But if you have them being evenly split between the two sides, it's nonpolar. You can also think about this as like having a negative and positive pole. And you can kind of see that the two sides have different charges there. But when we make them the same electronegativity, there is no pole. The electrons are evenly shared between the two sides. And so like this molecule, when it's nonpolar and you have a positive negative side, it doesn't really matter. They're not feeling attracted to either positive or negative charges. But if you make it have charge, sudden partial charges, they're going to want to interact. Like the partial negative side is going to be attracted to positive charges, right? So that's one way of thinking about molecule polarity. You can also have multiple things kind of coming together. And so like if I make A really electronegative and these things not very like electronegative, um, the electrons are going to spend most of their time around A, right? And these other things are not going to be quite as important. But maybe C is pulling on the electrons too. And so in this case, this is kind of like water, where we've got like two oxygens and or two hydrogens and the oxygen. Um, Maybe I think in that case it would be something kind of like this, yeah, because the oxygen is the negative charge. Um, so it'd be feeling attraction to the positive side, right? So that's the kind of like the idea. They don't apparently have this working with real molecules, but you can kind of play around with the electronegativity and think about that in terms of what the actual atoms would be, right? Okay, so that's the idea, is that these things that are polar, um, individually you can talk about a bond being polar, but you also need to think about a molecule and its polarity, which is a combination of all these different bonds coming together, which can be very, very important because they can kind of cancel each other out. And I'll refer to some of this stuff more in on my notes as well. But if you see right here, like this is a central atom with two things on the opposite sides. If these are the same strength, they're going to kind of cancel each other out with this geometry, with linear geometry. If the two bonds are equal and opposite like that, they cancel each other out. But if you have something like this, where you've got an electron pair on there, like this might be like sulfur, oxygen, oxygen, and then an electron pair. So you've got this trigonal planar. And in that case, these things shouldn't be able to cancel each other out anymore. It's just not going to work out that way. It doesn't matter how strong or weak these things are. If we've got like sulfur and oxygen, oxygens are going to be more electronegative. So you're going to have like kind of a negative side and a positive side there. So it can be pretty important to look at like these things and their bond angles, as well as the actual bonds and their polarity. So it's not just the individual bonds polarity, but you have to think about the geometry of the molecule. And this is kind of like water. Water, yeah, it's got like hydrogen, hydrogen, oxygen. And you might think that the two hydrogens kind of like cancel each other out. But because we've got the electron pairs on the oxygen here, they can't. Like it's like if you were to pull two strings, like some block, and you're pulling it with two strings. If they're not on the opposite sides, but they're kind of off like an angle, they're just gonna pull the object down in that case, right? So this is gonna have some partial charge, and this is gonna have some partial charge. With water, it's like the oxygen, the hydrogens. So the oxygen has more negative charge, hydrogens have more positive charge. So you see like some positivity down here and some like negativity up there in terms of the geometry of the molecule. So it's kind of helpful to be able to see these things, because they can show like, yeah, sure, even if the bonds did cancel out, geometrically they don't cancel out when you've got a bent shape. So it's important to look at the shape as well as the polarity of the bonds. And here, like, for example, they have that water. So we've got the oxygen and the two hydrogens. Um, or like we've got methane here. And in this case, methane, sure, these are polar bonds, but they're all being pulled equally, and they're geometrically canceling each other out. You could imagine attaching four strings to a ball and pulling on them with equal force. And if they're at this angle from each other, they cancel out completely. It's kind of neat. It's pretty cool actually in my opinion. This guy though doesn't completely cancel out because yeah, these bonds might be polar, but they don't geometrically cancel each other out. Like with nitrogen and hydrogen, nitrogen's got to be more electronegative, hydrogen's got to be less electronegative. So the electrons are going to spend most of the time around the center and the top here. So this molecule ends up having like a top part that's electronegative and the bottom which is electropositive because the hydrogens aren't really holding on to their electrons very much. They're kind of giving them all to the nitrogen. So you have that partial charge on the top that's negative and on the bottom that's positive. So you can kind of see these simulations, they're pretty important for understanding if something's polar and nonpolar. This thing, yes, the individual bonds between the phosphate and the chlorines, they may be polar, but it looks like they geometrically cancel each other out. Like these three in the plane, in the trigonal bipyramidal, like you can kind of see these three are in a plane with each other. They're going to kind of cancel each other out in that plane. And then you've got one kind of pulling up, another one pulling down. So they're going to cancel each other out as well. So that's just a neat little thing that you end up seeing there with the things canceling out. But you have to be careful because they don't always cancel out. And that can be kind of confusing sometimes. But you got to either draw it out or think about the simulation to think if they cancel out. This is a really good simulation for showing how the charges that we have on these things, like the negative and the positive charge, how that affects the boiling point. So we can start the simulation at a certain temperature and observe the phases, right? We can add an energy and make it be slightly different amounts and make it change its phases, right? And we can also make this into a nonpolar chemical and observe the same thing. And what's interesting here is that I've got almost no energy in here and it's moving a lot quicker. So when we have nonpolar things, the interactions are much weaker. It's easier to break those interactions and get to the next phase. And so if you add an energy, the molecules get moving faster pretty quick. So you can see that here, that as I add an energy, these things are moving a lot quicker than if I had nonpolar. So if I just start at like that beginning temperature, that looks pretty solid. That looks more like a liquid, maybe even some gas starting to come off. And we can set this up to like 150. Yep, definitely a gas. And we can make this go up to like 150 and see what that looks like. It's starting to turn into gas, still mostly liquid. So you can see that the polar things, they have stronger interactions, which hold them in at that previous phase for longer. You need more energy to get to the next higher energy phase. So that's kind of what's going on with polar and nonpolar. And they're showing these interactions with these dotted lines right there. In reality, I would do the dotted lines for these guys a lot thicker because they should have some really strong interactions between the polar molecules if they're showing it that way. There is also a interesting simulation here. This is having to do more with biology, but there's some chemicals that will have like part of the molecule has charge and part of the molecule is nonpolar. So you'll have like a polar and nonpolar end. And in that case, like the nonpolar end will go towards the nonpolar solution and the polar end will go towards the polar solution. So this happens with like fats and like your cell membrane and all that stuff. Molecules can have zones of polar and nonpolar, but we typically only see that in like a biology class. In a chemistry class, they don't really talk about this very often. It's either polar or nonpolar. We're usually talking about much smaller chemicals as well. So that kind of, this only works when you have very large organic chemicals like fats and like other things like that. When we talk about intermolecular forces, there's a lot of words, and I think that people will just get overloaded, honestly. So you need to think about how all these words are related and build like a mental map of how they're related. So I'd challenge you to do that for a second, and then I'll show you how I relate them. Basically, there's two parts here. And I've had students say like, there's too many different types of interactions. It's either polar or nonpolar. That's the big picture. Like chemicals either gonna be polar or nonpolar. And when we're talking about something being polar, we're talking about the charge. So there's some sort of charge, either positive or negative, or partial charge, which we show with this little symbol here. It kind of looks like a D with a line over it. And these things are going to interact strongly, kind of like magnets. So charges are going to be attracted to each other very strong. And so when you see the word dipole, you should think two poles or two charges. And whenever we have something that's polar, this is something that has a pole, kind of like a north or a south pole, which you can think of as like the positive and the minus charge. That's the main idea. So either something has poles and charges or it doesn't. So when we're talking about something that's um, polar or having a pole, these are going to have strong interactions. And hydrogen bonds, this is just a type of dipole-dipole interaction. So if you can think, okay, these are both four polar molecules, hydrogen bonds are just a type of dipole-dipole interaction, that's very helpful. So if we have like water, it's going to form hydrogen bonds with like other water, right? There's going to be some other water here. There's going to be some electrons on one side and a lack of them on the other. And you can see that there's a whole lot of electrons on this and not very much on this side, and so they get attracted to each other. So there's a pretty strong connection between water, and this is why water is so special. It has very polar, very strong interactions that are given a special name called hydrogen bonds, which is kind of weird because we don't really call these interactions bonds besides the strongest one. Um, yeah. Well, so when we're talking about polar, the electrons are being unevenly shared between the two sides. So the more electronegative thing, the fluorine in this case, is going to get the negative charge, the partial negative charge, and the thing that's less electronegative is going to get a positive charge on it. Now you only have nonpolar molecules when things are evenly split. So this could be like two of the same atom. And these are always symmetrical because they have to be evenly splitting things, right? So when you see van der Waals and London dispersion forces, big picture, they're the same thing. In reality, there's some slight differences, but big picture, these things are nonpolar molecules and how they interact when we're talking about van der Waals and London dispersions. So if you see names, that's nonpolar stuff. So if we're talking about something that's polar, this would be like the HF. This has partial charges, and they like to interact with water fairly strongly. These are pretty strong intermolecular forces. And so I've drawn in these gray dotted lines to show this hydrogen is kind of interacting with that oxygen and that oxygen as well. And so you'll see a ton of water molecules kind of go around these charges and try and stabilize them, try and make electrons not be so negatively charged, but kind of neutralize them with the protons in their molecules by getting them close. So if we're talking about nonpolar, now this is if you've got like, let's say this is, I don't know, like a carbon atom, and it's got like 4 electrons in it. Now those 4 electrons, they could be anywhere at any given point in time. They're just somewhere around this carbon in this shell, this electron shell. It could be just kind of evenly distributed, or it could all be on one side, or somewhere in the middle. These things are moving around independently. So at any given moment, you might have them all kind of on one side. You can see all the electrons are kind of on one side here. And so when we have all of our electrons on one side, even if it's just for a brief second, that can push or pull other electrons in nearby molecules. So let's say that, you know, these things, they're flying around, these electrons are just moving around freely, and then we look at this one right here, and all the electrons are on one side, and the atom that's nearby, basically these electrons get pushed away from negative charges. And if we were talking about a molecule over on the other side, the electrons would get attracted to the positive partial charge here. And so they can cause like this little chain reaction of other partial charges. And these are very, very brief. They're very, very temporary. They don't last very long. And so these are very weak in compared to actual charges. So you can think of this as also, oh yeah, there's also one thing to keep in mind, and we'll talk about this a little bit more soon. But if you've got these bonds that are canceling out, like these 4 different hydrogen bonds, they're kind of canceling each other out, or these 2 double bonds of oxygen, they kind of cancel each other out in terms of the polarity of the whole molecule. You can consider this to have like kind of like a positive inside and, or a negative inside and positive outside in this case. In this case, I think it's a positive inside and negative outside charge. And in that case, that's going to cause some nonpolar interactions, even though the polar bonds are in the chemical, they cancel out, and so you're going to have like these nonpolar interactions with other things. Also, if you've got a bigger molecule, there's going to be more electrons to be uneven, and so you can have stronger forces. So this effect of, oh, maybe they're over here or over there, bigger molecules, you can have bigger partial charges due to just moments where there's more negative on one side. So there is some stuff to be said there where like bigger molecules are going to have stronger forces with this stuff. So the big picture on this, just to reemphasize what we just went over there, is chemicals are either going to be strongly interacting due to polar interactions, or weak due to nonpolar interactions. And they're polar if they've got things that are different in their electronegativity, like fluorine and hydrogen, making them have those partial charges. Now, there's also something that's pretty important to consider when we're talking about if you've got 2 similar molecules, the one that's larger, like this guy, it's going to need more energy to boil than that one. Because this is a bigger molecule, you can think of it needing to go faster to change phase, to turn into a gas. So when we're talking about 2 similar chemicals and they've got similar like bonds in them, the bigger molecule is going to need more energy to boil. So that's important for those questions when they're talking about boiling point and melting point. It's the same thing with melting point. Bigger molecules will need more energy to melt for the same reason. So if we're talking about difference in polarity, like they're similar sizes, they've got similar molar masses, the molecules weigh a similar amount, but they have different atoms in there. We want to think about the polarity. And if something's polar, it's going to need more energy to overcome those stronger interactions. Because remember, this is going to have that partial negative charge, some partial positives as well. Because this has those partial charges and it's going to interact with other partial charges from other molecules, like there's going to be some other of these CH4Os. These molecules, they're going to be interacting with others. So they're going to need more energy to take this. Like this is going to need more energy, and this is going to need less energy to boil off. Same thing if you have like bromine bonded to itself, that's actually a gas. Like we know that that's a gas at room temperature. This is going to be um, like a nonpolar thing. They're not going to be interacting very strongly with the other bromine gas molecules. So they're going to boil off very easily, have very low boiling points. It's as opposed to HBr. If we were to take that compound, this is actually, I think it's an acid, and I think it's a solid in room temperature if you don't dissolve it. So this needs a fair amount of energy. So this is going to need more energy because it's polar. Because this, in this case, we've got the negative and positive charge kind of unevenly distributed in that compound. So there's a number of things to keep in mind. And one of the last things is if the bonds cancel out. So if we have, go back to that simulation, I think, yeah, they've got CO2 here. So this carbon dioxide, the carbon is going to be positive, the oxygens are going to be negative relative to each other. And so you can have, like, in the center, kind of a positive core and a negative, like, outside or two sides to it. But if you were to draw a line of symmetry through it, the charges should cancel each other out no matter how you cut it. And so these things are nonpolar molecules, even though they have polar bonds in them. So you can also, I want to just kind of highlight how I've drawn the bonds in here. So there's this arrow. If you do the plus side, that's the more positive side, and then the arrowhead goes towards the more negative side. That's just kind of the convention with those. And I think we saw that also in this simulation. They had that. And look, that's that partial charge symbol as well. So you should be able to recognize those symbols and what they mean. And in this case, this hydrogen, there's four of them kind of canceling out with each other. And so you've got that negative core and positive outer shell of positive charges around it. This thing, though, if we look at this SO2, it's a trigonal planar, I believe. This is what we were talking about right here. Yeah, this is trigonal planar. And you can see that the oxygens, the bonds can't cancel out because they're not opposite sides from each other. So that's going to be an issue and cause some polarity due to it essentially being bent. This is actually a tetrahedral shape, but this is what we would call a bent molecular shape because we've got the tetrahedral with the electron orbitals, but if you don't consider that, this is bent. So when we have something that's bent, it's most likely polar because you can't really cancel out these guys with those bonds there. So that's another way of thinking about this and kind of visualizing what's going on with these electrons being shared between the two sides. There's also this idea of like dissolves like. You've probably heard that before, where polar dissolves polar. So if you had like H2O, that's going to dissolve other things pretty well. They're like H2S. You can also dissolve charges very well, like polar dissolves ions because ions are charged. So these are like the partial charges. So the partial charges are going to actually dissolve ions pretty well. So like water dissolves NaCl very well because that likes to ionize to those two ions. That dissolves pretty well. So one way of thinking about this is that by dissolving, they're increasing the number of strong interactions between them. If you have something that's polar and nonpolar, The polar things, they're going to maximize their positive and negative interactions if they're all next to each other. Like these guys right in here, they're going to be able to interact with more charges if they're all bundled up together. That's why polar things end up not dissolving in nonpolar solutions. And vice versa, nonpolar things, they'll kind of block the spots. If you have like this polar thing and it wants to interact with this other polar molecule, you don't want like some nonpolar thing blocking the way. So what ends up happening is these nonpolar molecules, they end up just getting pushed all into one corner, essentially, where they're not interacting with all the polar stuff. So you get more strong interactions by sequestering the nonpolar molecules into one spot, so they clump together. So that's kind of what's going on with polar and nonpolar when we're talking about like dissolves like. And also the same thing with ions. You want to increase strong interactions, and dissolving, if things dissolve, that means that they're increasing stronger interactions. Like if we wanted to look at the same sort of scenario, if we've got like that plus and minus charge, those things like to have partial charges near them, right? So we'll have these partial charges kind of coming in. I think I should probably do that like purple to be consistent with that being polar. Yeah. So you could consider this where there's these partial charges interacting with actual charges, and those are pretty strong interactions as well. So the more charged something is, the stronger the interaction. So ions and dipoles, very strong. Dipoles and dipoles, pretty strong. If you have a hydrogen bond, that's a strong version of a dipole. So that's going to be kind of in the middle there between your charges. Then you got hydrogen bonds, and dipoles and dipoles. And then you're going to have like your nonpolar things. They're very weak in their interactions. One other thing that's pretty important, this relates more to biology. Hydrophilic means water loving, and hydrophobic means water fearing. And so oftentimes you'll see chemicals that are amphipathic, and so they've got part of the molecule is polar and part of it is nonpolar. And this is like that, kind of like those fats that we were talking about earlier. And so it will have part of it which wants to be interacting with nonpolar things, and part of it that wants to interact with polar things, kind of like what we were talking about here earlier. And so if you've got amphipathic, let's make that orange. What ends up happening is that amphipathic ends up kind of forming at the boundary between nonpolar and polar things. And so this is actually why we use soap, is that soap actually helps you kind of dissolve or break down polar and nonpolar things with each other. Like I like to think of amphipathic as like soap, because that helps you break down stuff and dissolve it in water that normally wouldn't dissolve in water, because water is polar. There's a lot of stuff that's nonpolar that you can't break down, but then you put soap on it and it helps it kind of dissolve into little packets a little bit better. So big picture, I know that's a lot. Big picture, you've got two levels. There's strong and weak interactions. Those strong are like polar, like your hydrogen bonds and dipoles and charges. And then your weak are your nonpolar things, which are typically like the same atom bound to itself, or something where there's some symmetry and things cancel out. So you got to be careful with that as well. And then also mass is relevant as well, because heavier things need more energy to change phases. Mass doesn't really, I don't think, come into play when we're talking about things dissolving or not. It has more to do with like the boiling point and melting point. So these are the typical problems that you'd see on like a college test or like an AP test. So if we look at this liquid hexane, they're asking about miscible. This is another word for dissolve. And they're asking which one is it going to dissolve best with. So this is just thinking about, is this polar or non-polar? So if I look at that, that's going to be like a long chain of carbons and hydrogens. This should be non-polar. So the question is, which of these things is non-polar? Is non-polar. That's basically what they're asking at us with this question. So if we're thinking about what is polar or non-polar, let's say we've got the NaCl. That's going to be aqueous, so that's going to be ions, right? So that's that part A. So that's kind of what we would see with that. So all the electrons are chlorine. They're not with this guy at all. So this is definitely polar, or like this is actually ions. So this is very like strong type of interactions. It's not going to do very well with dissolving that thing. So if we talk about B, this would be, yeah, basically you have to think about drawing these things out and looking at their geometry if you want to think about if they're polar or not. And I just kind of know my atoms, and so I know how to draw this one out. Like I know fluorine's going to contribute 7 each, so they need 1 more each. Nitrogen has 5, so it can give 1 each with 2 left over. So it's kind of also like NH3. It has the same sort of format there. So if we look at this, these bonds, they're all going to be polar. These two things, nitrogen and fluorine, they are different atoms. They're going to hold on to the electrons differently. And if we look at the periodic table, fluorine's over here and nitrogen's over here. So fluorine is more electronegative. It's going to hold on to electrons a little bit stronger. And so you'll end up seeing this partial charge that's unevenly distributed. We've got like a partial charge there and a partial charge here. And so this should be also polar. So this isn't going to work very well at dissolving that. It would rather be interacting with other NF3s than interacting with this guy. So they won't dissolve very well. So let's say that we've got C here. C is water. You should know that that's not just polar, but it's a very strong type of polar interaction because you've seen it a lot in this year, hopefully, of chemistry. So this is actually an H bond. So it's pretty strong compared to other things. So this might dissolve even worse than that. Like this, it's kind of hard to say which one of those is more has bigger partial charges. But we do know they both have partial charge. So then this last one, CCl3. So we've got Cl4, I think actually was what it was. Yeah. And in that case, we're going to have 4 chlorines. They're all around it. Something like this. Once we've drawn this out, it's pretty clear that this is a tetrahedral shape, and these should all cancel out to me when I look at that. And I see the chlorines, those are more electronegative than the carbon, and so they're going to hold on to the negative charge. They get most of the negative charge. The carbon's mostly positive, so it's kind of like a partial charge of positive on the inside. Oh, that's weird. And then negative on the outside, but because they cancel out, this is a non-polar chemical, and therefore this part D would be the most miscible. This would be really good at dissolving that, because remember when we talked about this, like dissolves like, polar things will dissolve other polar things easily, but if they're different, non-polar and polar, they don't dissolve very well. So then there's also this question 26. I got this from one of my students that I tutored. That's why it's all marked up. Sorry. But you can see we've got different melting points. And these chemicals, they are a little bit different in terms of what atoms we have. And the as you can see, N, A, and F, that's very big. So that's most uh, polar. And so if we look at Na and F, if we look at that on the periodic table, got sodium and fluorine, they're very far away from each other. So it makes sense that this is going to take the electrons away from that very easily. And yeah, they'll be very, very polar, and it'll be very hard to make that thing boil. So this is very strong, hard to boil. And then if we look at KCl, K and Cl, so chlorine isn't quite as electronegative as fluorine. So that's part of the reason there. The fluorine's just super, super electronegative. So you get a lot of stability from it getting those electrons. And then Rb and Br, where are those? This is even less electronegative. And Rb, yep. That, yeah. So these things essentially are getting to be less electronegative. And so there's less of a difference between the two in terms of how much they're holding on to electrons. And it's good that these are somewhat similar in size because mass will also affect boiling point. So it's good that these were all like single the first column, and this then all the halogens, right? Because they're similar size and the molecules weren't much bigger, we should be able to compare them based off the strength of the bonds interactions. Okay. And then there's a third one here. This is kind of tricky. Whenever they draw these things, each one of these points is a carbon. And if they haven't drawn anything else off of it, it's assumed that there's hydrogens bonded off of it. So if you've not seen that, that's kind of what's going on with these drawings. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So yeah, this all has the same number of carbons. But there's a slight difference in how these things are arranged in terms of their boiling points. So we've got this one thing here that's nonpolar. So that's going to be very quick to boil off. That's going to be very, very quick. And then if I look at these guys, we've got our chlorine and our OH. Yeah, those, let's think about that. So if we think about that, this is hydrogen bonding. So that's very strong, right? And then this isn't H bonding, but this is polar. But it's a slightly weaker version. So this, I think, is going to be next. And then it's a question of which one of these is going to be boiling off the longest, or take the longest to boil off. I think that this, yeah, this one has more surface area to interact with, like nonpolar things, I believe. So I think that this would be 3. That would be 4. That'd be the hardest to boil off because it's got the strongest bonding. And there's actually I think I might be getting these two mixed up. It might be 3. Yeah, this has like more area that it can clump up to other nonpolar things, so it'd be harder to boil that off. So I think that's the case. Yeah. All right. Thank you for joining me. This has been Andrew McLaren. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about, and remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia, and if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.